Look, I hope you're excited. You really should be. You've been through 80% of the course and it's all been building up to this moment. Today, you will be training your own proprietary LLM for fun and for profit. It all starts here. So, what is actually involved in today? We're going to start with some stuff that maybe isn't so thrilling. We're going to talk hyperparameters one more time. I've got some essential hyperparameters to go through with you. And the reason this is so important is that you're going to be doing some hyperparameter optimization yourself, the fancy word for trial and error, and you need to understand the context of what it is that you're playing with. And this is really the opportunity to build something that can beat other models. It's about understanding what kind of levers you've got to experiment with. That is at the heart of the R&D behind building leading models. So we've got some hyperparameters to talk about, and then we're going to set up a supervised fine-tuning trainer, an SFTTrainer, which is the sort of core object behind running this training, looking at part of the TRL library from Hugging Face. And then we will kick off our own proprietary LLM training process. It's going to be great. So first of all, though, before we get to the great stuff, we do need to talk about some of the essential hyperparameters that control this process, starting with QLoRA, and most of this is stuff that you're very familiar with now. So the first hyperparameter I'll mention is one more time to bring up the target modules. And I think you now remember exactly what this is. If you have an architecture of a transformer, a base model like Llama 3.1, it's way too big to try and fine tune this enormous great architecture. So instead, we pick a few layers in the architecture and we call those layers the target modules. They're the ones we're going to target. We freeze everything. We're not going to try and optimize these weights. There's too many of them. Even in these target modules, we're not going to train these. Rather, we're going to have onto one side a lower dimensional matrix that we will train this lower dimensional matrix and we will apply it to this original target module. We'll apply it, in fact, by multiplying them together, using that as a delta on the weights here. And so we train these little guys and we apply them to the target modules, selected layers in the bigger architecture. That's target modules. And then R, with this great 3D goggles as the logo, as the icon, R is how many dimensions do we have in this lower dimensional adapter matrix. It's often common with language learning tasks to start with 8. For this project, you're going to see I've got 32 as the R because we've got so much training data that I figured we could use quite a few parameters to learn on. But if that's running out of memory for you, you can have 8. I should say that the difference between 8 and 16 and 32 was quite marginal. It did improve things, but not by a huge amount. So if you have any memory problems, then stick with an R of 8 if you're on a smaller box. That will be just fine. 32 is splashing out a bit, but it was worth it given the amount of training data we have. Alpha, you may remember, is the scaling factor. It's used to multiply up the importance of this adapter when it's applied to the target module. In fact, you may remember there are actually 2 LoRa matrices. One's called LoRa A and one's called LoRa B. And the formula is that the change in weights is actually alpha, the scaling factor, times A times B. As simple as that. That's the most maths that we're going to get in this course, and I think that's not taking it too far. So that's as simple as what alpha is. It's the scaling factor, and the rule of thumb is have alpha to be double R. That's what everyone does. By all means, you can experiment with other values of alpha, but the norm is to do alpha as 2R. So we're going to start with an R of 32 and an alpha of 64. Quantization, of course, is just what we call it when we reduce the precision of the weights in the base model. The base model has 32-bit numbers in it. We reduce it down to 8 bits or even down to 4 bits, which sounds insane. We did that with our base Llama model, and we saw that we were still getting results. They weren't great results, but I think that would be true for the base model overall. And we did see actually that the 8-bit model did better than the 4-bit model, but they were both pretty miserable at it. By all means, you can try training with the 8-bit model too, but we're going to train with a 4-bit model because that's what will fit in our memory. And but I'd be interested if you try the 8-bit to see whether you get significantly different results. And then the final hyperparameter is a new one that we've not talked about before, except to show you it in the code: dropout. So dropout is it's a technique that's known as a regularization technique, of which there are a few, which means that it's a technique designed to prevent the model from doing what's known as overfitting. And overfitting is when a model gets so much training data, it goes through so much training, that it starts to just expect exactly the structure of the data in the training data set and then give back exactly that answer. And it starts to no longer understand the general trends of what's being suggested, but instead it sort of hones in on precisely those words and the prediction that comes later. And as a result of that, if you give it some new point that it hasn't seen in its training data set, it performs really badly because it's not been learning the general themes. It's been too much learning the very specifics of this training data set. I'm being a bit hand-wavy again, but hopefully you get the idea. That's called overfitting, when you are too precisely adhering to the training data set and the outcome, and it's not learning the general flavor of what it's trying to predict. And it's that flavor, it's that nuance of what's going on. That's what you're trying to teach the model. So that's the preamble, the explanation of what overfitting is. But now to tell you exactly what dropout does, and it's really simple. What dropout actually does is it quite simply removes a random subset of the neurons from the deep neural network, from the transformer. It takes a random percentage. We're going to start with 10%. It takes 10% of the neurons and it just wipes them out. Sets their activations to 0 so that they are not involved in the forward pass or the backward pass. They're not involved in predicting the next token, and they're not involved in optimizing. It's as if they're just not there. And as a result, every time that you're going through training, the model is seeing a different subset, a different 90% of the neural network. 10% of them have been removed randomly each time. And so the weights are sort of discouraged from being too precise and looking too precisely for one set of input tokens, but instead, because different neurons participate every time in the training process, it starts to learn more the general theme than learning very specifically how to expect different tokens. So it prevents any one neuron from becoming too specialized. It supports this concept of more general understanding in the neural network in this very simplistic way of just removing 10% of the neurons from the process, a different 10% each time. So that's dropout. It's really very simple when you realize it. It's literally dropping out a bunch of the neurons. And the norm, but it's usually somewhere in the range of 5% through to 20%. I've picked 10% as the dropout that we're using. You should absolutely experiment with 5% to 20% and see whether you get better results or not. It is very much a hyperparameter to be experimented with. Okay, so those are the 5 hyperparameters for QLoRA. Next time, we'll talk about 5 hyperparameters for the overall training process. So I'm now going to talk about 5 important hyperparameters for the training process. And some of these we've talked about briefly before, but many of these will be somewhat new to you unless you've worked in other data science projects of this sort. And the first one I'll mention is epochs, which we did briefly mention some time ago. So epochs are referring to how many times are you going to go through your entire data set as part of the training process. So you might imagine that when you're training, you take each of your training data points and you go through the set once and then you're done. But in fact, it turns out that you can get more mileage by going back a second time and going through all of your training data again with your model. Now you might think, why does it help to go through a second time when the model already saw it once. You're just giving it the same data a second time. Well, remember, when we go through the training optimization process involves going through each of these points and then making a very small step in the direction of making the model a little bit better, shifting the weights in our LoRa matrices a little tiny bit so that next time it does a bit better. So every time we go through all of the training data set, we have an opportunity to get a little tiny bit better. And presumably once it's gone through once, the model is now in a bit of a different state. So when it sees it again, it can allow it to refine and do a little bit better. There is another reason why it often makes sense to have multiple epochs, and that comes down to batch size, the next hyperparameter. Batch size is saying that often we don't take one data point and put it through the forward pass of the model to predict the next token, calculate the loss, and then go backwards and figure out the gradients of how much does that loss, is that affected by the different weights in the parameter in the model, and then optimize the model by doing a little step in the right direction. It sometimes makes sense to do that at the same time with a bunch of data points together. Like often you pick 4 or 8 or 16 and you do it together for all 16. One reason for doing that is performance, that it means that you can just get through everything faster. You can do it all together. If you can fit 16 data points on your GPU, then that's a good thing to do. There are some other reasons why it might actually be better to do it in batches than to do it step by step. But the basic reason is for performance. When you do multiple epochs, with each epoch, it's typical that you resort, you juggle up all of the batches. So they're different batches, different sets of these 16 data points that the model sees with each of your epochs. So actually, in some ways, the data is different for each of these epochs because it's seeing a different sample of your data points as it goes through them. And that's another reason why multiple epochs can be good. Now, there's one very common technique, which is to, at the end of each epoch, you typically save your model. And it's quite common to run a bunch of epochs and then test how your model performed at the end of each of those epochs. And what you often find is that the model was getting better and better as it learned more and more in each epoch. But then you reach a certain point where the model starts to overfit, which we talked about last time, where it starts to get so used to seeing this training data that it starts to solve just for exactly that training data. And then when you test it, the performance gets worse because it's not expecting points outside its training data set. So you start to see like better, 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 worse, 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 and then the results get continually worse. And what you do is you run this and you quite simply pick the epoch which gave you the best model, the best outcome. And that's the one that you consider the result of your training. That's the version of the fine-tuned model, and that's what you take forwards. So it's common to run a larger number of epochs and then use that kind of testing to pick which one was your best model. With that, I will pause and continue with these parameters in the next video. Continuing our adventure through hyperparameters for training, the next one is pretty crucial, and it is called learning rate. And again, many data scientists amongst you will know this one only too well. So for very, very quickly, for those that are less familiar with this, again, the purpose of training is that you take your model, you take a training data point, you do what they call a forward pass, which is an inference where you go through the model and say, predict the next token that should come. And it gives a prediction, the predicted next token. Or in fact, it gives probabilities of all of the possible next tokens. And you use that and you have the actual next token that it should have actually been. And you can take these two, the prediction and the actual, to come up with a loss. How poorly did it do at predicting the actual? And what you can then do is take that loss and you can do what they call back propagation, when you go back through the model and figure out how sensitive, how much would I have to tweak each weight up or down in order to do a little bit better next time. And then you have to take a step in the direction. You have to shift your weights a step in the direction to do better next time. And that step, that amount that you shift your weights in a good direction so that we'll do a little bit better next time when faced with exactly that training data point, is called the learning rate. And it's typically, it's either 0.0001 or 0.00001. You will see some examples when we go through it. And there's also an ability to have what's called a learning rate scheduler, which is when you start the learning rate at one number, and during the course of your run, over the period of several epochs, you gradually lower it and lower it and lower it. Because as your model gets more trained, you want your learning rate, the amount of step that you take, to get shorter and shorter and shorter until you're only making tiny adjustments to your network because you're pretty confident that you're in the right vicinity. So that is learning rate. Again, it will be old hat to many people who have a data science background. It might be new to others. Gradient accumulation is a way, it's a technique that allows you to improve speed of going through training, where you say, okay, so what we're going to do is we normally do a forward pass. We get the loss as I just described it. We then work out the gradients going backwards, and then we take a step in the right direction, and then we repeat. Gradient accumulation says, well, perhaps what we can do is we can do a forward pass and get the gradients, and don't take a step, just do a second forward pass and get the gradients and add up those gradients, and do that a few more times. Just keep accumulating these gradients and then take a step and then optimize the network. And that just means that you do these steps less frequently, which means it can run a bit faster. In some ways, it's a bit similar to batch size. It has there's some sort of a conceptual similarities there because you're sort of grouping things together and just taking one slightly bigger step. In the hyperparameters that I've set up, I'm not using gradient accumulation. I've got that set to 1, but I did try it in the past and I see how it speeds things up. And so you might well be interested in experimenting with that and see what it does. So that is gradient accumulation. And then last but not least, the optimizer. The optimizer is the formula that's used when it's time, when you've got the gradients, you've got your learning rate, and it's time to now make an update to your neural network to shift everything a little bit in a good direction so that next time it's that little bit more likely to predict the right next token. And the process for doing that is called the optimizer. And there are a bunch of well-known formulae for how you could do that, each with pros and cons. You'll see we pick one in particular that's one that is a little bit more expensive in terms of the performance. It's a bit harder work, but it leads to good outcomes. So it's the one that I would recommend starting with. And then if you do end up having any kind of memory problems, there are alternatives that consume less memory. But that process is called optimization, and the algorithm that you pick to do it is called the optimizer. And it's another hyperparameter in that you can try different ones and see how they do. So I realize it's an awful lot of talking, and I've also used the conversation about hyperparameters to explain a bit about the training process. But hopefully this was good foundational background that's prepared you for what is just about to happen now, which is we're going back to Google Colab, where we are going to set up and kick off our SFTTrainer to fine-tune our own specialized LLM. Well, I'm sure you're fed up of me saying that the moment of truth has arrived, but it really has. The moment of truth has arrived. I'm extremely excited, as you could probably tell, and I hope you are too. This is a big deal, a big moment for us. So first of all, we are in the week 7, day 3 collab. And I must confess that I'm doing something a bit naughty in that I have picked a super beefy A100 GPU box, which is the most pricey of the Colab boxes. It gobbles up 11.77 compute units per hour. And I think the current going rate, if I'm not mistaken, it's roughly 100 units cost about $10. So this is spending about $1 an hour right now. Those prices do change from time to time. Yeah, this is definitely not as cheap as things usually are, and you don't need to do this. You can definitely use a let me see. Change runtime type. You can be using a T4 GPU. I will tell you which parameters to change for that, and it will be just fine. But if you don't mind spending a few dollars and you want to have a blast and you want to be changing hyperparameters and training fast, it's beautiful to have an A100 box for a while and experience the raw power of a box with 40 gigabytes of GPU RAM. So I love it. I don't mind giving Google a little bit of money for this, because it's such a treat to have a juicy, powerful box like this. So anyways, we start with some pip installs. This includes this library TRL, Transformers Reinforcement Learning, from Hugging Face, which contains the SFTTrainer, Supervised Fine-Tuning Trainer, which is the trainer that will be doing the work for us today. And I do want to say, I should take just a moment to say that I talked in the last video a fair bit about training, and I sort of did it almost by the by. I talked about some of the hyperparameters, and in doing so, talked about a bit of the training process of forward passes and backward passes. And again, for some people, that's old hat, that you're very familiar with this. For some people, that might have gone over your head, and you might be saying, you know, can you not take more time to better explain the whole training process? And one thing I do want to say is that Hugging Face has made this so accessible, so easy. They've made the barrier to entry for training a model so low that whilst it's very helpful to have an intuition for what's going on in terms of optimizing, of taking steps in the right direction, this is helpful. It's not essential to know the detail of the theory. You just have to know enough to be able to tweak the hyperparameters. Hugging Face makes it incredibly easy to do the training. So if you did feel like some of that went over your head, then rest assured it really doesn't matter. The code will make it very clear. And if you know this stuff back to front already and you're very familiar with optimization, then great. That will make it so much the better. It'll make it even easier. All right. So we do some imports, and now we have a bunch of parameters to talk about. So the base model, of course, Llama 3.1, 8 billion. We know it well. The project name. So this is the project name that will be used in weights and biases when we get to that to show the results that we'll compare, and we'll also use it when we upload to the Hugging Face hub. And I'm using the name Pricer for this project, as in something that comes up with prices. You may remember when we were training GPT, I called it Pricer GPT. I've kept the project separate because the results will be so different that just because we'll be measuring different quantities, it will be confusing to have them in the same project. So I've called this just Pricer. Hugging Face user, you should put your Hugging Face name in here because you'll be wanting to push your fine-tune models to the hub for your models because you'll treasure them and use them in the future. And you can keep them private. They're just for your own consumption. So when it comes to the data, we need to load in the data set. And here you have a choice. If a few weeks ago when we were doing data curation, you did go all the way through and you uploaded the data set to your Hugging Face hub, then you can keep this line in here and it will have your Hugging Face username and then Pricer data, which is what we called it, and you'll be able to load it in. Alternatively, if you decided just to watch that one out and watch me doing the dataset stuff, but you didn't upload it to Hugging Face, then shame, but still I do understand there was quite a lot to it. You can simply uncomment this line where I've just hard-coded, we don't need the F there, I've just hard-coded the Pricer data in my hub, which will be made public, so you can just download it there for fine. You don't need to upload your own one. And then maximum sequence length, you'll remember the data is always crafted so that it's no more than 179 tokens. adding on a few tokens for the start of sentence and any gumph at the end means that we're going to say maximum sequence length of 182. And this is very important because every training data point will be fitted into this. And this needs to be a small enough number to fit in our GPU's memory. And that's why we've cut off our descriptions to fit within this amount. So then a few sort of administrative things. I've come up with something called the run name for each of these runs, which is quite simply the current date, the year, month, day, and hour, minute, second right now of this run. And you'll see why in just a second. I'm going to have something called the project run name, which is pricer, and then a hyphen, and then the date. And then the hub model name, where I want to save the model, will be the username, and then this here. And why am I doing this? So sometimes people like to just have one model, and as you run this, you just upload different versions that you store against that same model repository. Because remember, everything in Hugging Face is just a Git repo. So you could just keep, you could basically just keep pushing new versions of your model that will just be just new versions of that, like checking in new versions of code, pushing versions of code. It could just be different versions of the model with the same model name. But I quite like to separate out my different runs and have them as different models, because within them there'll be different versions potentially as different epochs, and I like to keep them separate because I'll have trained them with different hyperparameters and I want to keep note of that. So that's the way I like to do it. Not strictly necessary, but I find it helpful. And just to give you a sense for that, if I just take if I take the run name, let's start with that. If I just show you what run name is right now, the run name you can see is just the current date that I'm doing this, the 22nd, and the current time. That time is in UTC here in Universal Time. It's not actually 4 minutes past midnight. So that's the run name. And then what was the other thing? There's project run name and then hub model name. So project run name is just pricer followed by that. And then hub model name, which is what it will be uploaded as, is that. So this will be creating a model with that name after it's run. And so when I look in my models directory, I see a bunch of these because I've run this too many times, more times than I'm willing to admit, but it's been great fun. I've got lots of these pricer models, and they've all been running. So just to finish this off, I see it just disconnected and reconnected over there. So the hyperparameters then that we are using for QLoRA training, you know are, well, the dimensions of the matrix, and I'm starting with 32, as I say. You can bring that down to 8, particularly if you're running on a lower box, it'll be just fine. LoRa alpha should be double R, and so if you bring this down to 8, then make this 16. The target modules, of course, are, you know it too well, I don't need to tell you what they are. And this is the standard ones for the Llama 3. These are the modules that you target. The LoRa dropout was the thing that I gave quite the long explanation of last time. It's the trick to help with regularization or with making sure that models generalize well to new data points by taking 10%, in this case, 10% of the neurons and just wiping them out. Setting their activations to 0, effectively just removing them from the training process, a different 10% each time. And as a result, the model doesn't become overly dependent on any one neuron. It just learns to generally, for the whole model to get better at receiving training points and giving the right next token. So it helps the model generalize. 10% is 10.1 is a very typical starting point. You should try 5% and 20%. And see how they perform. And quant 4 bits true is quantizing down to 4 bits. Okay, the hyperparameters for training. I've set this up to run for 3 epochs. You could do it just for 1. By all means, you'll have perfectly decent results after 1. Batch size, I've got to 16 right here. I would you need it you with a juicy A100 box. I can pack in a batch size of 16 batches. Given that this is the max sequence length, it can cram all of them in and still have just about squeeze that into the 40 gigabytes of memory. But for you, if you're going to go with a lower end box like a T4, then this should be probably 1. You could try it higher if you get more GPU memory that's still free. There's this convention that people tend to use powers of 2 for batch size. So 1 or 2 or 4 or 8 or 16. And in theory, there's various loose bits of evidence that suggest that if you have it as a power of 2, the GPU is better able to parallelize it, and the performance is slightly better. But there's always the data on that is always just a little bit vague. And so generally speaking, I imagine if you can cram a little bit more batch onto your GPU, then you should do so. So I wouldn't shy away from having a batch size of 3 if you can fit that on your GPU. It's going to run faster than a batch size of 2. Maybe 4 would just be that little be a bit more efficient if it could fit. But I think the general advice is just whatever will fit on your GPU is what you should pick, and start with 1 and see what kind of headroom you have, unless you're splashing out like me, in which case go for 16. Gradient accumulation steps, I explained that last time. I think actually this helps with improve the memory of the process. You could try, but I'm staying with 1. You can try that at 2 or 4 as well. Learning rate, I think, understand is super important, is how much of a step you take as you optimize to try and take a step in the right direction. And learning rate is a super important hyperparameter that you need to experiment with. And it's one of those things which there's no right answer. Learning rate could be too high or it could be too low. What you're trying to achieve, this is going to be a bit hand wavy again. What you're trying to achieve is if you imagine that the loss, the loss of your model is something which has a big dip in it like this, and you're trying to find this valley, you're trying to locate this valley, then you want to be taking these steps along the direction of the valley dropping so that you will end up at the bottom of this valley. If your learning rate is too high, you might jump over that valley and jump back again and never actually go down into the valley. If your learning rate is too low, you might take little tiny steps and be making too slow a progress towards that valley. There's another problem with taking too small steps. Supposing that you don't just have one big valley, but you have a smaller valley and then the big valley. If your learning rate is too low, you might take small steps and end up sinking down into that little valley. And actually, every small step you take just goes up the 2 walls of the little valley and never gets out of that little valley. And so you never realize that there was this much bigger valley just next door. So that is a key problem. It's a common problem with learning rates being too small. People call it being stuck in the local minimum. This thing is called a minimum, and it's local to where you are, and you haven't found the global minimum, which is all the way down here, because you're stuck in the local minimum. And that is the problem with having a learning rate that's too low. There is this nice trick. I picked a learning rate of 0.0001, 1 times 10 to the minus 4. There's a nice trick of using something called a learning rate scheduler, which is something that will vary the learning rate and make it get smaller and smaller and smaller over the course of your 3 epochs until it's pretty much 0 by the end of your 3 epochs. And you can give it, if you choose to use one of these, you can give it a different shape. And cosine is a very nice one, which starts with a learning rate that starts at the slowly decreases, and then it decreases quite a lot, and then it tails off at the end. You'll see that visually in a moment, and that's a really good technique. And the final learning rate parameter is called the warm-up ratio, which is saying at the very beginning of your training process, things are quite unstable because your model has a lot to learn from the first few data points. And it's quite dangerous to have a big learning rate initially because it would jump all over the place. So warm-up ratio says start with a lower learning rate and then warm it up to the learning rate that it becomes the peak, and then start your cosine trail. And you'll see that visually, so it'll make more sense. But these are very sensible settings, but you can definitely experiment with a higher or lower starting learning rate or different scheduler types. And finally, the optimizer. So here I am picking the paged Atom W. W means with weight decay. A paged Atom W 32-bit. That is a good optimizer, which has good convergence. It does a good job of finding the optimal spot, but it comes at a cost of consuming memory. I put down here a link to a Hugging Face write-up on the different optimizers that you could pick. It's clear that the most common for transformers is Atom or Atom W, and that Atom does do well because it stores the rolling average of prior gradients, and it uses that rather than just the most recent gradient. But of course, by storing that, that's going to take an extra memory footprint, and so it's a bit greedy for memory. So if you're running out of memory, then you have an option to choose a cheaper, less greedy optimizer to save some memory, but the results might be slightly worse than using the paged Atom W. Okay, and then finally, some administrative setup. This number of steps is how many batch steps to take before it saves progress to weights and biases to show us how things are going. And this is how many steps before it actually uploads the model to the hub and saves a proper version of it. This is whether or not we're logging to weights and biases. So that is a tour of the parameters. And in the next time, we really get to the trainer itself. It's time for action, everybody. We've set up our collab. Here we are, week 7, day 3. We've got our constant set up. We've checked our model name, and it's time to get into things. So the first thing we're going to do is log into Hugging Face, which you know well. And then after we've logged into Hugging Face here, we're going to do something that you don't know so well, which is new, which is logging into the wonderful Weights and Biases platform. So you may have already set this up as part of last week's foray into Weights and Biases, but if not, it's very simple to do, and of course it is free. You go to the Weights and Biases, WandB.ai, right linked here. You set up a free account, and then you can find your WandB API key, your Weights and Biases API key, and then you have to go to this padlock symbol here and add it in as a secret to your Google Colab. Or if you don't want to do that, you can also just type it directly into the notebook right here instead as well, but it's recommended to use the secrets. So once you've set up Weights and Biases, on we go. We then load in the data set, and we can just quickly check that the data set is what we expect. We expect there to be, let's have a look at how many training data points. We're looking for 400,000 of them. There they are, 400,000 training data points, a lot of them. Let's look at the first one, just make sure it's exactly what we expect. It should be the text in this training data point is the prompt we're expecting, followed by the price right here. And it's going to be this that the model is going to be desperate to predict this next token and get it right. And we also have the actual price here. You can see we're rounding it to the nearest whole token, and we tell it that we're looking, how much does this cost to the nearest dollar? The nearest token, the nearest dollar. And there is the price, the real price. If we look at the test data set, not that we'll be using that today, but you'll remember the test data set is very similar, just one tiny difference. There is not a price after here. It just says price is dollar. And that is what we're training our model to be good at doing. Okay, so if we're logged in, if we're asking to log to Weights and Biases, it then sets up the Weights and Biases project. This is in fact not required to have this line of code, because actually Hugging Face will do this for you if you start to run and you haven't run this line. But I sometimes add this because you can also, if you wish, pass in a config with some parameters, and that lets you set up some extra attributes that will appear in Weights and Biases. That's a useful trick to know. But anyways, you can run this or not. It doesn't make much difference. Okay, so then this we saw before, we're just going to take this hyperparameter and decide whether we're going to use the bits and bytes config for 4-bit quantization or for 8-bit. And we are, of course, going with 4-bit. We're going all the way down. And then it is time to load in the tokenizer and the model. And so usual code to load the tokenizer. I mentioned to you that this is boilerplate stuff that you do that tells the trainer that we want to pad every data point so that it fills up our maximum sequence length, and it should pad it all up with end of sentence tokens just to fill up that that set of characters, the 182 length of our tokens in our sequences. So it will pad them to the right with these tokens. And then there's this one line here, which is just another boilerplate thing to set the pad token ID on this thing called the generation config. And the reason that put this in there is it stops it saying a warning later that it doesn't see this, but I actually think it's would take this anyway. So this avoids it printing an unnecessary warning. And then we end by printing the memory footprint as usual, and we see that it is the 5.6 gigabytes that we expect for our 4-bit version of the Llama 3.1 8 billion parameter model. Okay, one more technicality here, this thing called the data collator. So there is this this cunning thing that when we're doing our training, we're going to be passing in the full sequence, including the price, and the model will see lots of examples of this and get better and better at predicting these tokens. But there's a bit of a catch. We actually don't care for the model to learn about how to predict all of the tokens in the prompt up until the $sign. We want it to learn how to predict that token right there. So we don't want it to spend lots of time seeing how good it is at writing descriptions of products and then also learn the price. We want it to focus on that price. And doing that involves setting up something called a mask. When you tell the trainer that you don't need it to learn about the prompt, you just want it to take this into account to give it context, but learn how to predict this token right here after the $sign. Setting up masks is a bit fiddly and involves a bit of messing around with tokens. But luckily, Hugging Face has made it very easy indeed with a nice little utility that does it all for you. And it's called the Data Collator for Completion Only LM, which is what we've got. We've got something where all we want to do is have it complete this particular sentence. How it works is you come up with something that's called the response template, which sounds very fancy, but it just simply means what is the chunk of text which is going to indicate that I want you to predict whatever comes next. And in our case, it is quite simply price is $sign. We want it to predict the next thing after that. So you put that into something called response templates, and then you create an instance of data collator for completion only LM, passing in the response template, and you also have to tell it your tokenizer. And it will use that to build the final set of masked data that goes into the trainer. And you'll see that in just a second. So this is super simple, and it's doing something quite sophisticated behind the scenes and making it easy for us. All right. And finally, the last big moment for us. This is going to look like lots of code, but there's not actually that much to it. We are about to call our trainer, and we're going to have to pass in 2 sets of parameters. One of them is called the LoRa config. It's the hyperparameters that relate to how we're doing our LoRa training. And the other, the SFT config, is the supervised fine-tuning config. Is just general stuff about how training should work. And what I've done is I basically set these things up to pull from the constants that we defined right at the top of the notebook, like alpha and dropout. And then the things that don't matter so much, I've just put in here what to use, and these are not important hyperparameters, or they're just things where we should set it to a certain value. So you can see that for the LoRa parameters, we of course pass in the alpha, which we know well. I won't define it yet again. The dropout and the target modules that we're targeting. So that goes into the LoRa config. The training parameters, the SFT config has stuff like the run name, how many epochs are we running, the batch size, super important. 16 in my case, it might be 1 for you if you're on the T4 box. The gradient accumulation, that is 1 for us, and then things like learning rate, the cosine scheduler that we decided to use, And then just down at the bottom here, we're saying that we want this to be pushing to the hub every time that it's doing a save, which is every 5,000 of the batch steps. We want it to push this model to the hub so that we'll get a series of saves to the hub, and we can see our model at each of those points. And we ask to give it this name, and we say we want it to be a private repo so that it's not public yet until we're satisfied that we've got great results from it. And then this is the final line. We set up something called an SFTTrainer. We pass in just a few simple things. Number one, it needs to know the base model. What is the underlying model that we want to fine tune, which is Llama 3.1. Number two, what is our training data? We pass that in. What are the LoRA parameters? This has, as you know, it has the alpha, the R, the dropout. The tokenizer, the training parameters that we just set up right here. And finally, we pass in that collator, which is that sneaky object which knows to look for the prices $, and it's telling it, don't bother predicting what comes before that. Worry about what comes next. And so this then will have set up our trainer. And in the next video, we'll run this single line, fine-tuning.train, which is the line that kicks it off. That will be quite the moment. So without further ado, let's go do that. The moment has arrived. Here we go. We're in fine-tuning. We do fine-tuning.train. There is also a line here to push it to the hub after it's finished. Let's kick that off. So while it's kicking off, we'll take a quick look. The GPU is starting at 6, which is what we expect. It's about as much as it needs for the model itself. And it's going to be warming itself up and getting ready for this training. While it's doing that, since we're waiting for it just for a second, I might as well just talk to some of these other training parameters that we didn't mention before. Eval strategy. So it is typical when you're doing this kind of training that you would repeatedly have a held out data set that you would use for evaluation, that you would use as a constant set that's not involved in training, that you would use to get the model to validate that it's making progress. Now, I've not done that here, partly because we've got so much training data that I think it's got plenty to be training on just in one epoch alone. And partly because the speed of training was so important, I didn't want it to be stopping to do validation repeatedly through this. But it is a best practice to have a validation data set. We've got plenty of data for it. We held out 2,000 test data points, so you can use a bunch of them as part of your validation step test set. So one certain improvement to this that would be more of a best practice would be to use an eval strategy and pass in validation data as well as training data. But it wasn't super necessary in this case, so I didn't do it. Okay, well, you may notice if you are glancing over this way that the GPU memory has shot up, and out of the 40 gigabytes of GPU memory that I've got, 38.2 is currently being used. So I really did squeeze this so that with 16 batch steps, a batch size of 16, I would really use up almost the entire GPU, very close to running out there. And you can see that stuff is happening down there. So let's just scroll down and see what we're seeing here. So it's off and running. And we can see that things are happening. And now to run the entire 3 epochs is going to take, according to this estimate here, just over 24 hours, 26 hours or so. So, you know, it is something like 8 hours per epoch on this, even on this beefy machine, because the training data is so enormous. But it's not strictly necessary to go through all 400,000 training data. And as I say, you can run this on a much lower end box and let it run for a while, and that is all completely fine. But what you're seeing here is it's off every 50 steps, just as we configured. We're getting an output that shows us our training loss so far. And this is now running and outputting to weights and biases. And in the next video, I will give you a peek into how that's looking. Actually, slight change in plan. I'm going to wrap up the day 3 at this point, and say that we'll take day 4 to look at the results in weights and biases and to examine the progress of training, because I think that we should let it run for a bit and then take some serious time to do that. I'll also at that point be able to show you the model in the Hugging Face Hub. And I feel like I might have been a bit glib about the amount of money that it costs to train these models. I want to be clear that you really don't need to spend any material amount of money to have a lot of fun with this and investigate hyperparameter optimization as part of this course. It would only cost cents. And so I want to quickly explain how you can do things like reduce your training data set to a more manageable size and have more sensible parameters so that you could train on a normal spec GPU box and be spending only a few cents on this project. That's all that's required. If you wish to be a complete nerd like me and go all out and run lots of runs with top-end boxes and spend $5 or $10, then on your head be it, as it will be on mine. But it's not necessary at all. But you do need absolutely to take a moment to congratulate yourself on where you've got to. You have a training run happening, I do hope, right now. While I speak, it is running. And you are in a position now that you can explain QLoRA pretty well for fine-tuning open source models. You're so fed up with me talking about target modules, I'm sure. And now explaining things like learning rates, R and alpha, and dropout, and all of the various other things like optimizers and the like. It's all second nature to you, and it's all complex stuff. This is upskilling in a big way. So congratulations. It's tremendous progress. And next time we'll go over to weights and biases and see what's happening.